So we have been talking about the connectivity. This is the number 7 handouts of the connectivity. Um, so this one is already talking about the structure of two connected graph. But before moving on to the two connectivity, I want to kind of cover something that I missed last time. So there is some concept called edge connectivity. And vertex connectivity. Okay, so we will start with the one that we are more familiar with. This is kappa. Kappa of G is the minimum number of vertices whose removal will separate the graph.就是拿掉几个点，可以把它打坏了哈，就。So it will be much easier to just look at the example. We have seen this. This graph has kappa equal to 1 because you can just pick the middle vertex. And try to draw some more examples, then it can help you to understand better about this concept. Cycles are good structure actually. So if you want to break the cycle, you need at least 2 vertices. So for a cycle, kappa is equal to 2. But then there is a weird case, which is called the complete graph. Complete graph Kn, it has n vertices, and it has n vertices with all pairs of vertices connected. So you take out one vertex, 2 vertices. No matter how many vertices you take out, it is still there. It is still connected. So it is a weird case. So in this case, we say it is kappa equal to n minus 1. It's just a weird case. Okay, so in many books, people don't really want to define what is the connectivity for a complete graph. Okay, and there is another parameters called lambda, and lambda is called the edge connectivity. Kappa is called the vertex connectivity. Okay, and you can easily guess what's going on for this parameter. It is talking about how many edges is required to break the graph apart. So it is the minimum number of edges whose removal will separate the graph. So it is another easy concept. You just look at the graph and try to break the graph apart by taking out some of the edges. So for example, the one we had before, kind of the two cycle on the left hand side, right? Previously, we can just take out one vertex. But if I ask you how many edges to break this graph, then you need to use at least 2 edges. You can use something like this. Right, so lambda is equal to 2. And same for a cycle. You can have lambda equal to 2. And for complete graph, this one is okay. You can think of a complete graph on 5 vertices, then you can take out 4 edges, then it is fine. So it is n minus 1. The only weird case is how about K1, but just ignore that. So K1 has lambda equal to 0, but I don't know how to explain it. Okay, I will use the space at the very bottom to recall this parameter. It's called the delta of G. It's the minimum degree. Yeah, and then that's all I want to say, right? It's a minimum. Yeah, I don't have anything else to say. It's just the minimum degree. So each vertex has its degree, the number of edges that is adjacent to it. So this vertex has degree 2, degree 2, degree 2, degree 4. 每一个点它那个度数就是旁边有几条边连上去。Okay, so you see if here is 2, 2, 2, 4, 2, 2, 2, then minimum degree is equal to 2. So suppose you have a vertex whose degree is equal to the minimum degree. Like you have a vertex here, and it has 2 edges going outside. Then you can just take out all the edges at just instant to that, and then you break the graph apart. So by taking out all the edges instant to one vertex, then you got a separating set of edges. So naturally, we have the minimum degree is an upper bound for the lambda. Okay, whenever you have a minimum degree, then you can find a separating edge set. Okay, so so actually there is a relation between all these parameters. This is from the numbering of the textbook. It's one of the proposition that any graph like what I said, the minimum degree is an upper bound for the lambda. But actually, lambda is not so strong as the vertex connectivity. If you take out some vertices, you can take out a lot of edges, right? So it kind of tell you the idea that you can take out the edges, you can take out the vertex. It's easier to break the graph apart by taking out some vertices. So think about why it is true. if necessary, you can go to the textbook and check out the proof. But I think it is more important to give you an example where all the parameters are different. Okay. So you know, as long as there is a vertex like this, it's kind of the central vertex. If you take out, then the graph becomes two parts. Then the connectivity, the vertex connectivity is always equal to 1. But imagine every graph looks like this, right? Whenever the graph looks like this, it has a kappa equal to 1. But how about the edges, right? I think it is not too hard to generate a graph such that you need 2 or more edges whose removal will separate the graph, right? So then I construct this graph that on the left hand side you have 2 edges, on the right hand side you have 2 edges. If you want to take it, if you want to break the graph, then you have to take out at least 2 edges. Now finally, if you check out this graph, the degree is 3, 3, 3, 3, and the middle part is 4. So the minimum degree is equal to 3. And you can try to build your own example. It wouldn't be that hard. The idea is to kind of keep a vertex in the center and then try to increase the edge connectivity, and then you will very soon realize that you can build a super big graph and whose delta is very, very large, but with low edge connectivity. Right? For example, this kind of thing is called a bridge. Okay. And if you have something on the left hand side, something on the right hand side, and there is only one edge in the middle, a bridge, then lambda is equal to 1. And it's very easy to just create a graph that has a high minimum degree. Okay. So every vertex has a lot of edges incident to them. But there is a bridge. So lambda is equal to 1, and delta can be as large as possible, whatever you want. So we have such an inequality, but the inequality is not tight most of the time. Now we know a bit better about the connectivity and the edge connectivity. We want to move on to the structure of the graph. And that's also the purpose of this course. Although we call that as the topological method, but basically we want to understand, investigate the structure of a graph. And you will realize that lots of graph has a good structure. It is just not random. It has a nice structure there. So let me show you something more. Let's start with the one connected graph. Okay, so basically we focus on one connected graph or connected graph. Say, yeah, okay. Now a vertex V is a cut vertex of G if the set V itself is a separating set, is a separator. Recall that a separator just means that you can separate the graph, and it is a vertex set. So something in the middle, this is the cut vertex. And you can have several cut vertex. And now the block is a little bit weird to define. So instead of giving you the description, let's look at one example, which is on your handout. Okay, so give me some time to draw the same graph on your handout, and you can just look at that. If you look at your handout, then you will see a graph on 8 vertices. And this 8 vertex graph has 2 vertices that is drawn with black color. Right, so these 2 black vertices, those are the cut vertices. It's easy to check it out, right? But then you will realize that such a graph has some nice structure, right? So what I meant is you can see that after taking out the vertex, it looks like the graph has several parts. Okay, the left hand side, it looks like a diamond or whatever you call that. You have 4 vertices, and it looks like it is a good structure. And if you just look at this graph, if you just look at the part that is enclosed by the blue circle, then it is a 2 connected graph, right? And there is no cut vertex of this graph. 我强调一下，就是这个图里面它是没有自己的 cut vertex， 它当然包含了大图的 cut vertex， 但是它没有自己的 cut vertex。那个黑点是大图的。So you see that this graph, it does has a cut vertex, but this is a cut vertex of the whole graph. But if you just focus on this one is not a big deal. It is not a cut vertex of itself. It is a cut vertex of the whole graph, but it is not a cut vertex of itself. And same here, for each of the part, you can kind of draw that. It's ugly here. I think your handout has better printing. So the cut vertex is like the boundary. Then you can partition the graph into several parts. And each of the parts has a good structure. By good structure means that the reason that I draw it like this is because there's no more cut vertex inside. Okay, so a block is anything like these 4 cycles. 4 parts. A block is maximal induced subgraph without subgraph edge, without any cut vertex. So in this graph, the black dot, or in here it is white, the dot, it is a cut vertex. And every of these blue circles, those are just called a block. So really, you look at this, it's like a natural structure. It is called it's called a block decomposition, and we will build a block tree from here. Okay, so let me see if I can squeeze in all the things here. Okay, so let me move on to block tree. The key is the blocks has a tree-like structure. Okay, let's define, say, B. This calligraphic B is a set of blocks. So, for example, we have 4 blocks. We have B1, it is the left-hand side. We can say B2 is the middle part. We have B3, it is the one that is vertical, and B4, it is the triangle part. It is a bit small, sorry, if you cannot read it clearly, try to let me know. So blocks are graphs, and this is a collection of subgraphs, right? A collection of blocks. Then we can talk about C, this calligraphic C. What is the C? It's the set of cut vertices. Let's call that as X and Y. So in this graph, we have 4 blocks and two cut vertices. And you can build a graph like this. You can draw the cut vertex first, and then let me use a different. I draw a square, but it's just a vertex. Okay. I draw a vertex which represent the block B2, and there is a B3, and there is a B4. So it's natural that you see X is instant to B1 and B2. So you draw an edge from B1 to X and B2 to X, and you see Y touches B2, B3, B4. So Y is instant to B2, B3, B4. So this structure will record what happens in the bigger graph, and it is always a tree. It is also a bipartite graph. You have 2 parts, which is this B set and the C set. Okay, and the details of this definition, just look at the handout, and you should be able to understand that. So unfortunately, I haven't been able to cover 2 connected graphs, but it's okay. I will stop here.